Shawna Hollen from the University of New Hampshire. Professor Hollen got her PhD in 2012 from Brown University and then spent the intervening years at Ohio State University as a postdoc. She's here to talk to us today about atomic Legos. And the floor is yours, but I'd like to give you a token of our gratitude for coming. I don't know.
Okay, I won't make everybody wait. I will think that now. Thank you, and I'm very glad to be here. Thank you for inviting me to come out. It's good to see another campus in the Northeast and visit with some people in the physics department here. Recently imported from the Midwest, but originally from Oregon, so still getting to know the area. Okay, so as I said, this is not my daughter, but I do have a daughter about this age, so now I need to replace this picture. But the way I normally start is, this is not literally me as a child, but this is me as a child. And so you can imagine how excited I was when I saw that this is an entire field of physics. So these are van der Waals heterostructures of two-dimensional materials. So you can create entirely new crystals now just by mechanically stacking two-dimensional layers of crystals on top of each other. And this new crystal now has its own set of properties. So this is what this is the motivation for the things I'm going to be talking about today. Okay. So first we have to talk about what a two-dimensional crystal is. Obviously, there's a single atomic layer, and that atom has some thickness. So what do we mean when we say two-dimensional in this case? So to answer that question, you have to ask, where are the electrons and what are they doing? So this is graphene. This is the most well-known two-dimensional crystal. It is carbon atoms bonded in this hexagonal lattice, and this is what the electron bonds look like. And so if you look at that in a two-dimensional sheet, you see that this third dimension is entirely quantum mechanical. And everything, all of the electrons are moving only in the two-dimensional plane. So this completely changes the way this material behaves. And it actually changes when you go from a bulk material into a single layer. You've broken a real symmetry in the lattice. So you've changed the electronic properties fundamentally by taking it to this two-dimensional limit. And graphene is a pretty remarkable material. Even in a two-dimensional sheet, it's a very good metal. It's actually a semi-metal. And it has good properties for potential electronics. Electrons in graphene have a high mobility, so when you push them with an electric field, they move very easily. And they can travel really large distances without scattering. So you can actually do ballistic transport experiments at room temperature with graphene. So that means you push an electron on one electrode, and microns later, it arrives without scattering. And also because of the unique band structure of graphene, which I'm not going to get into, the electrons in graphene behave like they have no mass. So you can do relativistic type experiments with electrons in graphene as well. So all of these materials came out of graphite, which is something we thought so little of that we use it to write with pencils. So graphite itself has not found as many exotic areas as graphene. And two-dimensional materials can touch on a large number of fields in physics. So quantum transport, this is an example of that. This is the quantum Hall effect in the graphene, which is enabled by this unique band structure. And you can also do spintronics with two-dimensional materials. This is an example of a spin valve. So here you're looking for coherent behavior of the spins. So you inject spins and use them, push spins across a device and measure the spins on the spin-only transport on another electrode. And this is an example from Optical Electronics in a different material. This is molybdenum disulfide. And you can, because of the band structure of this material, it's a semiconductor, but it also has a spin polarized band. So using a laser, you can selectively Using the circular polarization of the laser, you can selectively excite electrons of a certain spin direction. So that's a pretty interesting feature in that material. And finally, for electronics, I only have to show this image, and actually I should update this because this has been in progress still, but this is a graphene screen showing ice age, seems like. Okay, so this is our 2D crystal toolbox. So of the library of two-dimensional crystals, we can access metals, something that acts more or less like a metal. Boron nitride, which has the same crystal structure as graphene, except that the atoms in the lattice are alternating boron and nitrogen. And this breaks a symmetry and makes this material into an insulator, pretty wide bandgap insulator. And then there's molybdenum disulfide, and now we are looking at a single unit cell rather than a single atomic thickness. But it still behaves like a two-dimensional material. And this is a pretty good semiconductor. And then I'm going to mention graphene is another type of insulator because I'm going to be talking about it later. So graphene is graphene, except you now have hydrogen atoms bonded on each of the carbon atoms in alternating up and down pattern. And this makes graphene, which was a good metal, into a pretty good insulator. Okay. So now you can imagine taking these materials and putting them together in stacks to make totally new materials and devices. And bulk semiconductor heterostructures gave us LEDs, solid-state lasers, the quantum Hall effect, the observation of the quantum Hall effect, and topological insulators. And these materials are, these heterostructures are really difficult to make. They rely on epitaxy. And so there's a lot of effort in growing these materials on top of each other to make these heterostructures. Here we are really only limited by what we can mechanically stack on top of each other. So it is a kind of labor-intensive stacking right now, but we're not limited in the same way that we were for three-dimensional bulk heterostructures. So the question is, what will these mechanically assembled two-dimensional heterostructures bring us? Okay, so there's a number of examples out there already on 2D material heterostructures. This is an example of a lateral heterostructure, actually. There's a different material in the center than on the outside. So this is a junction of tungsten diselenide and molybdenum diselenide that forms an LED. And there are a number of other examples here that I'm just going to flash up. This is a field effect transistor. This is a model for a solar cell. Here's another solar cell and a p-n junction. And here's an example of a mechanically stacked crystal of two-dimensional materials. So this is bilayer graphene alternating with bilayer boron nitride. And you can see that you get these. This is a TEM image showing these nice atomic planes in the material. So there's another opportunity here that I want to point out. So imagine that you have this graphene material where you have the graphene but with this hydrogen bonding on each carbon atom up and down. So this whole material is an insulator. Now let's say we could go in there and selectively knock off the hydrogen atoms in a pattern, and then we would have, if we knocked off all those hydrogen atoms, then we would have graphene, which is a metal. So because all of the properties of the material are available on the surface, you can imagine just changing the structure of these materials from the surface to change their properties in a fundamental way. So now we can imagine writing two-dimensional circuits onto this two-dimensional canvas of materials. And this is just one example of being able to do that. And there are also other interesting questions here, because how many hydrogens do you have to knock off before you start seeing the intrinsic properties of graphene? So there's a heterostructure in here. And how wide does it have to be before it starts behaving like a conductor or a semi-metal again? Okay, so I'd like to pause here and just see if there are questions. Yeah.
So what's the advantage of knocking off the hydrogen as opposed to starting with graphene and just etching away the stuff you don't want?
I guess the advantage is that you could start with this whole, it's like a fabric of material, and you could write in whatever circuits that you wanted. You can imagine a capacitor plate with the thing that I drew as a resistor of some kind. And you can do this down to the atomic scale.
But I can take a graphene sheet and just cut away the parts that were graphene in your picture.
Okay, so maybe then the advantage on that would be the potential for doing more than just that, more than just insulator and metal. There are examples where you could make magnetic moments by bonding to the 2D lattice. So you could selectively make certain regions magnetic and non-magnetic, or semiconductor to metal, or metal to insulator. So it's, you know, there is a lot of creativity there that could be taken advantage of potentially. Yeah.
There are these iconic images of the IBM researchers pushing xenon atoms around on the surface display at IBM. Can graphene be manipulated in that way with a tip to?
So that's, I'm going to defer that question, so I can show you what we've been able to do so far. But there, aside from what we're doing, there are groups that are using hydrogen to do lithography, basically, in STM groups. So they use it as more or less as a mask on three-dimensional materials. So the technology is already there to some degree.
One quick question. You showed a beautiful crystal built up of bilayers of two different things. Is that like 3 years of work for a graduate student? How long does it take to actually mechanically make a substantial structure?
I don't know for that one in particular, but this field has been developing very fast, and now what people have in order to do this is a tool. It's a flake transfer tool, and it's under an optical microscope, and transferring a flake, it takes skill and practice, but once you have everything working, which is not a minor thing, but once you have everything working, the flake transfer itself only takes a minute or so. So you can imagine, you know, getting enough skill to make up a mechanical heterostructure that's many, many layers. And that is much faster than what people were initially doing, which is using polymers to transfer 2D materials and then dissolving the polymers and repeating that process over and over again. That's dirty and very slow. So even the mechanical stacking now is much more efficient than where it started, say, 2 years ago. Other questions? Okay, so then I have some questions for you. Okay. So these are one-atom thick materials. Aren't they dirty? The surfaces, they all have grime and water and all kinds of things absorbed on them. So what happens, how can we control these materials? And so the answer to this question is yes, they are. They're really dirty. And then the second question is, when you stack materials with different properties, do they keep their own properties or their properties mix? So if you stick a metal on top of a semiconductor, what's the net result? What do you get out of that? And it's not that simple, because these materials, although they are mostly only interacting by van der Waals forces, they're still interacting. So there are a lot of questions here. So the answer to this question is, good question. Okay, this is something that I'm interested in looking at. All right, so most of what I'm going to tell you about today are results from my postdoctoral work at Ohio State. I will tell you at the end about my lab that I'm building up at UNH. But this is the instrument I use for the results that I'm going to show you today. This is a low temperature STM. So I'll give you a little bit of a tour of what it's like to do these types of experiments. So we grow, for these experiments, we would grow graphene on copper 111 in UHV, and then perform STM experiments at 5K. So here's the tour of the chamber. This is the load lock. So I like to think about UHV chambers like reverse space. So if you were to go from space into your habitation spaceship, you would need to go into a load lock where you would then you would go into this small room, fill it with air, and then open the inner chamber. So this is the same thing in reverse. So when we want to put a new sample in the chamber, rather than venting the entire chamber, we put it in a load lock, and we pump down the load lock to 10 to the minus 8 millibar. And then there's a very long arm here that transfers the sample from the load lock into this chamber over here, which we call the prep chamber, and we use this chamber to prepare our samples. And this is at ultra-high vacuum, so 10 to the minus 10 millibar, or 10 to the minus 13 atmosphere, roughly. And then once we've grown the sample in this chamber, we use another long arm here to transfer the sample. We open a door, we transfer the sample into the STM chamber, and the STM, which I'm going to show pictures of later, hangs at the bottom of this big dewar. So this is a liquid helium dewar, and the STM head hangs on the bottom of that dewar, so it's at 5 Kelvin, roughly. Okay. And this is also at ultra-high vacuum. And then very briefly, I'm going to tell you about our growth of graphene on copper. So it's the motivation for doing this in ultra-high vacuum is that you can really well control what's on the surfaces. So this is very similar to an atmospheric pressure chemical vapor deposition growth, which is what a lot of people do to grow graphene, except that we had to make some modifications in order to do this in high vacuum conditions. So what we do is we weaken ethylene at 10 to the minus 5 millibar, very low pressure of ethylene, and we cycle the temperature of the copper substrate. This is the 111 face of the copper crystal. And we cycle the temperature up to close to the melting point of the copper, around 1,000 degrees Celsius. And this helps dissociate the ethylene on the surface. The carbons stick behind, the hydrogens flip away, and we repeat this process until we have enough carbon dissolved on the surface, and then we cool down the crystal. The carbon actually surface segregates to form this hexagonal network. So that's how we grow graphene islands on copper in ultra-high vacuum. And then we transfer this sample as quickly as possible from the prep chamber into the STM chamber, and so that it stays really clean. We do that. Any questions about this? So I'm probably not going to come back to this. Yeah.
What's the size of the islands?
I'll show you some images of islands. They vary in size quite a bit, from nanometers up to almost a micron. So.
What's getting them dirty inside an ultra-high vacuum chamber?
It's kind of amazing, isn't it? So one thing is that you're heating this surface up and cooling it down, and then you put it onto, then you cool it down. So you have to cool it down before you transfer it into the cold chamber to conserve liquid helium. And as it's cooling, anything that hits it's going to stick there. So you want that cooling process to happen really quickly. But let's see, there's a rule of thumb that you're going to have some number of particles hitting per minute. I think 1,000 particles per minute at 10 to the minus 6. And so then you can sort of, that's just a random process. So you can sort of figure out how many atoms are going to hit your sample and the time that you have to transfer it into the chamber. So even in ultra-high vacuum, and also since we're doing this growth at 10 to the minus 5 ethylene pressure, we can get ethylene molecules to stick on it and makes it gumpy. So yeah, it's clean, but even still, it's not perfectly clean. We'll see. Other questions? Okay, so I wanted to just take a minute to tell you a little bit about scanning tunnel and microscopy. I'm not sure if all of you are familiar with this technique. So on a macroscopic scale, you have a piezo, and you put a wire inside this piezo tube. And the piezo tube is, so a piezoelectric material is a material that deforms when you apply an electric field. And this is how you are able to control the movement of a wire down to the atomic scale. So this really enables the whole technology of STM. So you apply voltages on these electrodes on opposing sides, and that deforms the piezo so that the tip can do the scanning motion. So that's how the tip scans back and forth. On an atomic scale, what you're using is quantum tunneling of electrons to measure I'll say the distance to the surface in this case. So you have this, you have a tunnel junction between the tip, which is made up of atoms, and the surface, which is made up of atoms. And that tunneling current, the probability of electrons tunneling across that gap, depends exponentially on the distance to the surface. So that means that if you get this tip close enough to the surface, as you move it across these atoms, the tunneling current is going to go up and down and up and down and up and down, depending on how close the surface atoms are to the tip. So that's why you can have such high resolution of atoms on surfaces. Obviously, it's a little bit more complicated than that. And in particular, since you're using electrons to probe the distance to the surface, they're also going to be a probe of available states in the material. So if you were to image over this gold atom, say, maybe that gold atom has a higher density of states for electrons, so it would look like you would have a higher tunneling current there, and that wouldn't correspond to a change in height. So it's always this convolution of electronic properties and topographic properties that you're measuring. In reality, what we do is we have a feedback loop that holds that tunneling current constant, and then we control the height of the tip using the Z piezo. So we have the tip actually moves up and down and up and down and up and down across the surface as we scan. And STM is an amazing tool. Oh, I have the reference later, I forgot about that. This is the work, famous work from IBM, where this is a copper 1-on-1 surface and iron atoms, and you can see that not only are they imaging individual atoms on a surface, they are arranging them into a circle. And I'm going to talk a little bit more about what these ripples are later, but it's a perfect example of this convolution of electronic states and topography. So these are actually interfering electron waves that they're imaging on the surface. Okay. And of course, we thought circles were boring, so we wrote Swift, Ohio, with the same sort of atoms on cobalt atoms on copper 1-on-1. Okay, so if we want to write these two-dimensional circuits into graphene, what do you do? So I showed an image before of taking graphene and removing hydrogen atoms, but first we have to get graphene, this hydrogen bonded material. So let's say we have, this is one of our images, so this is a graphene sheet, and it's draped across two copper step edges. So these steps that you see here are the underlying substrate. And then these little bumps up here, I'm going to show more images of later, but these are actually defects in the graphene lattice. So we have these islands on copper. So what we do is we go in, oh, here's the image, sorry. And this is the carbon lattice here, just as a guide. And so you can get these really spectacular patterns just from, this is just from a single missing carbon atom. Oh, sorry, I'm going to show that slide again later, and I'll show you what I meant with the hydrogen plan. Okay, so this is another zoomed-in image showing you the scale of the graphene lattice that we're imaging and where the carbon atoms are. Okay, so this is the tour of the experimental system. This is an 800 angstrom wide image of graphene. So graphene are these nice smooth-looking areas on copper 1-on-1. And this is what I meant by UHV. It's still not perfectly clean. All of these black dots here are defects on the surface of the copper lattice. And these are step edges here. So this is a pretty big image. This is the largest image we can take at one time with the STM at helium temperatures. And if we want to map out what the area looks like, then we need to take an image and then move the tip over and take another image and then move the tip again and take another image. So you can do this and you can get sort of the map of the world according to the STM tip. So this is after you're imaging on the sample. You can take lots of these 800 angstrom images and put them together into a map. And this is the entire area that your STM tip can access at one time. And you'll notice that this entire region in the middle is empty. And that's because we started seeing these very high bumps here. And we don't want to go there because you could run into these features and destroy your tip. And then you would have a bad day. So this whole region, this whole map of the world is only 0.6 microns. And here are the graphene islands that I've shaded in purple. So they're definitely on the nanometer scale. And in ancient times when there were non-navigable parts of the ocean, they would write on the maps, "Here be dragons." So this is the STM version of "Here be dragons." This is one of the graduate students drew this dragon for me. And if you go there, you're going to crash your ship, and then you will have a bad day in the lab. So we try to avoid that. And so this is a view of the actual instrument through a window from the outside. And so let me point out some things to you. This is a sample holder. This little disc right here, that's the copper crystal itself. It's sitting on a heater, so that's how we get up to 1,000 Celsius. And then this small wire here, I can have a zoom. This small wire here, that's the tip and the tip holder. So this is where all the action is happening. This itself is really small. So to scale, here's the size of a penny. And let's take a closer look at that penny. So here's the back of the penny. Here's Abraham Lincoln. And here is a grain of salt. So using the grain of salt as a scale, which is about 300 microns, we can zoom in and say that the entire map of the STM map of the world that we were imaging, if Abe Lincoln was chiseled perfectly into the back of the penny, then that entire region would be the width of one of his hairs. So these are very small areas we're working with. And so that gives you a bit of a sense of what we see. So there we go. And another way to look at it is if you took a single pixel from this photograph of the back of the penny, you could fit 900 maps of the world in one pixel. So the amount of area that we're imaging on our crystal is incredibly small. Okay, so here's our map of the world. So how far in the other direction do we have to go to see atoms? These are islands. Okay, so let's zoom in on this island. This is a nice one. Okay, there's the island. Zooming in again. Okay, there's a pattern. These are not the atoms yet. We have to zoom in even further to see them. So this is where the atoms are. Anyone have a guess for what this other pattern is?
Copper lattice?
It has to do with the copper lattice, but it's bigger, right? You guys see this pattern? It's a Mori pattern. That's right. So it's a Mori pattern between the lattice of copper atoms and the lattice of graphene atoms. So if you've ever seen two window screens overlapping, you get a secondary pattern that's larger. And that secondary pattern can actually tell you a lot of information about the relative alignment of the two patterns. So if we know what the alignment of the copper lattice is, then we can find out the rotation of the graphene lattice on top of the copper lattice. So that's kind of a fun thing. Okay, so now, how do we use STM to write circuits in a two-dimensional campus? What do we do to do that? How might we achieve that? So we have our very nice pristine graphene islands. So all we need to do is go in there with the STM tip and zap it and deposit a hydrogen atom on the sheet, right? Seems reasonable. No? Okay. Okay, so we tried to do something similar to that. And first we did this control experiment. So this is a different surface of a copper crystal. This is copper 100. I'll tell you in a minute why we use this surface. And this is clean copper. Everything on the surface is some kind of defect, but there are pretty large clean areas. And most of these defects are carbon monoxide, which you just have it always hanging around in vacuum chambers. So it's going to be there in some amount. But here's a pretty clean region. So what we did was we dosed molecular hydrogen into the chamber, and this the sample is at 5 Kelvin. So the hydrogen absorbs in sort of a pseudo-organized way on the surface, and you can actually see the post-packed lattice that it makes. And then we needed atomic hydrogen, not molecular hydrogen. So we decided to try to create atomic hydrogen using, here's a zoomed-in view of this nice post-packed structure that you can image. So we decided to try to dissociate molecular hydrogen using the STM tip itself. So it's a very sharp, pointy thing, and we can apply a high voltage. So we applied about 60 volts with the tip pretty far away from the surface. So this is field emission from the tip to the sample until we got a 0.5 nanoamp field emission current of electrons. And this, we were able to show that this works. So if you look carefully, when I change the image, you'll see something new. Does anyone see it? So there's all these little black specks on the surface now, right? And there's still this molecular layer. There's plenty of molecular hydrogen around. So now we have something like this going on. And then, in order to get rid of the molecular layer, we heat the substrate up to 20 Kelvin. And this desorbs the molecular hydrogen layer. And we're able to get back to a clean crystal, but the atomic hydrogen stays behind. And we are convinced this is atomic hydrogen because of a very cool experiment that we were copying, where you can actually, if you look closely, look in one of these green circles. This is at 5 Kelvin. You can see these little dark spots jumping around, right? So what this is actually atomic tunneling from different, between different sites of the carbon lattice. And this is following some work that actually showed this is quantum mechanical tunneling and not thermally activated popping of atoms on the same system, this copper 100 system, where they dosed atomic hydrogen.
This is at 5K, you said?
This is at 5K, yeah. So we compared to that work, and we're convinced that we were seeing atomic hydrogen, and this was some of the most fun data that I've ever collected, is just watching these atoms tunnel around the surface. Yeah.
When these guys tunnel, this is a loop, obviously, or are they tunneling forward and backwards repeatedly?
This is a loop, but it's like 6 frames, so they can tunnel forward and back. I think it's 6 or 7 frames. And the way that that this was originally shown to be quantum mechanical tunneling was they did a temperature-dependent measurement and showed that at, I think it's 10 Kelvin, the tunneling rate is constant with lowering the temperatures. We didn't repeat the temperature-dependent part of the study because we were pretty happy with reproducing the results.
Could you do this with deuterium or tritium?
They did do it with deuterium in the original paper, which was blue, and I can't remember the rest of the records. I can find it later. And they compared the two.
Yeah.
And they saw quantum tunneling for hydrogen, but not deuterium.
How long did it take to do a complete scan?
So each of these images was about 3 minutes. So So it's not short, but not really long.
So the tunneling is a very long time scale.
The tunneling is a pretty long time scale, although we could be missing tunneling events in the wave range. Okay, so now we basically just repeat the same experiment, except on our graphene lattice that we drew. So we absorb the molecular hydrogen, and we do the high voltage. We apply high voltage between the tip and the sample, and then we anneal. And this is one of the results from that. So you can plainly see, aside from the fact that I colored it blue, you can plainly see that there is a difference between the surface in the left pristine island and the hydrogenated island. And if you zoom into this small region here, there's a pretty spectacular lattice that shows up. So it's got this almost Chicago maze structure in this case. We most commonly see a triangular lattice, and I'll show you that on the next slide. But this was very interesting. Okay, and then this process is also reversible. So if we image at a relatively high bias, about around 4 volts, we're able to remove the hydrogen layer. So this is the example of that, and there's some damage on the sample here from various other experiments that we were trying, but you can tell that the lattice has returned because there's you can see a moire pattern in the pristine island that's the same as this dehydrogenated island.
Isn't part of why you're going for graphene that it's an insulator?
Yes.
Isn't that going to shoot your STM in the foot?
No. I'll delay responding to that. It's a very thin insulator. Okay. So this is a second. We did this a number of times, and this is the most common result that we got that I'm about to show here. So this is a clean graphene area, and this is the copper over here. And after all of these steps, we ended up with this, which you can't see very well, but I'm going to zoom in a second, where there's a pattern over the entire area. And this is a comparison between the pristine graphene lattice with a particular moire pattern, where the lattice constant is 2.5 angstroms, and this hydrogenated graphene lattice that we most commonly get, which has a triangular structure as well, but the lattice constant is 4.2. And we're still trying to understand what these hydrogenated lattices actually are, where the hydrogen is. So that's what I wanted to tell you about this local hydrogen functionalization that we were working on. And the idea is to use hydrogen to locally functionalize graphene towards writing 2D circuits in a two-dimensional material. And there has been other work in trying to hydrogenate graphene and even some other STM work, but previous results are all disordered. So the fact that we were able to get something that looked like an ordered structure of hydrogen on graphene is the real difference between what we've done and what other people were doing. Okay, so then in the next few minutes I'm going to tell you about some electronic characterization of these graphene islands. And this is going back to the question of whether the resulting heterostructure between two materials is really the sum of its parts, or is there something more going on? Or how does graphene interact with the metallic substrate? So then going back to the STM explanation, you can look at, so I've already sort of talked about this, but just as a reminder, when you are tunneling with electrons into a material, you're tunneling into the electronic states. So you can use the tunneling current as a probe of the electronic band structure. I'm going to show you a little bit about how we did that. you always measure this combination of topography and the electronic landscape, like in this iconic example. Okay. And these are electron waves. This is a pretty awesome example of particles in box. Okay. So first we have to look at copper. So this is the substrate that we're using. And we're looking at this 1-1-1 surface of copper, which when you cut the copper crystal off at a surface, it can form what's called a surface state. And so this is the main structure I want to tell you about. So the blue shaded regions are the electronic states of the bulk copper crystal. And then along the 1-1-1 surface, you have this red band here. And so this is a surface state. And this appears because of the interface, the actual surface interface creates a different boundary conditions that allow for the creation of the surface state. But what's interesting about it is that it doesn't overlap with any of the other states in the copper crystal. So basically it's a band of almost free electrons. And that's what it's compared to over here. So these are electrons with some mass, some effective mass. And we can measure the surface state with STM. So here's a comparison of doing a point spectroscopy measurement on the bare copper over here and on the graphene covered copper. So what we're doing is we park the tip over the surface and we change the voltage between the tip and the sample. And that is changing the energy of the tunneling electrons. So you can control where they tunnel into. So if you watch these arrows as we move across, when the voltage hits this band, you see a jump in the density of states. So this y-axis here is the derivative of the tunneling current with respect to the voltage, which is proportional to the local density of states. So you can actually see this surface state onset in the tunneling spectroscopy measurements. And what you'll notice when you compare the bare copper to the graphene copper is that this surface state has shifted in energy. So it's been affected by the presence of the graphene. Okay, the other thing we can do, which is pretty cool, is image these scattering electron waves. So these are the same waves that we're scattering in the particle in a box image from the early work of Eiler and Kami. And here we have our STM work of electron scattering on graphene islands on copper. So these are STM images at different energies, and this is the corresponding DIDB map. So this is the local density of states of these electron scattering. And what you can see just by looking at the images is that the wavelength of these scattering electrons is changing with energy. Well, we can analyze that and do a Fourier transform, find the momentum of these scattering electron waves, and then plot them as a function of the tunneling, the energy of the tunneling electrons. And we get these very nice parabolic curves showing that these are behaving like free electrons with a modified mass. And the interesting thing that we found was that the effective mass of the electron scattering is significantly different on the graphene-covered copper regions than in the bare copper regions. So it's actually a lower, the electrons behave like they have a lower mass over the graphene regions than they do on the bare copper regions. So one way to think about this is that maybe the potential for the electrons that the electrons see on the surface of the crystal has been sort of flattened out by the presence of the graphene. That was kind of a fun thing to do. Okay, so there's also a second set of these surface states that we were able to look at. And this second set are these image potential states. And this is this is kind of interesting. They're at much higher energies, and they're formed like a hydrogen atom. So if you have an electron floating above a metal, it's going to have an image charge. And then it can form a bound state with its image charge, and then you have a whole set of energy levels based on that bound state. So that's what this is showing here. And they have, they're in a series like the hydrogen atom. And they are actually also physically floating above the crystal. They're not, so they're physically separated from the crystal. So we can probe these states by doing tunneling experiments at higher energies. Okay, so we look up here and we can compare. So now we have voltages. Before we had voltages from -1 to 1 volt. And now we're at voltages from 1 volt up to 10 volts. And we're looking at these. So we see these, the top is the tip height. So we do this experiment on a little bit of a different feedback mode where the tip keeps backing up because the current changes a lot. So this is the tip backing up every time it hits one of these. Every time it hits one of these image potential states, all of a sudden there are a lot more states for the electrons to tunnel into. So the tip keeps backing up to keep the current constant. And you see these corresponding spikes in di to d. And we can also here compare the copper, the bare copper, to the graphene copper. And we can get a lot of information out of here. One of the obvious things is that these image potential states are shifted. And this reflects a change in the work function between the graphene covered regions and the bare regions. And the other thing that we can see is that these resonances are much narrower. So that tells you about the electron lifetime in these states. How long are the electrons hanging around if they tunnel into the state? Because it's sort of a transient state, they have to then tunnel into the crystal itself. So we can actually get a lot of information about staring at these things. But, oh, here you go. So this is what's happening. But really, the summary of all of these spectroscopic experiments is, okay, what have we learned? We've learned that graphene is modifying the electronic structure of copper. We're not really probing the independent electronic structure of graphene itself, because it's too strongly coupled to the metal. So we saw in these experiments, we didn't see anything that was really independent of the copper. We were looking at how the graphene was affecting the surface states in the copper. And I can tell you a lot about the potential and the interaction between the graphene and the copper. But to us, it told us that it was important that there was copper nearby and graphene was changing the way the states above copper acted. So this is sort of a summary of how graphene modifies the surface states in copper. All right, so I put questions here, and then I have a slide or so after this where I'm going to tell you a little bit about what I'm doing at University of New Hampshire and what I plan to do in the future. But I thought I'd pause here in case you wanted to talk more about the work I just presented before I change gears. Okay.
Your method for producing atomic hydrogen involved bringing the tip in close proximity and putting a significant voltage across it. Presumably, you could also do this by introducing a large magnetic field, which would tend to spin polarize. In the cold atom world, if you have spin polarized hydrogen, that precludes H2 formation and you end up with atomic hydrogen. Has that been done?
No, I don't know of anyone who's tried that. It's an interesting idea. Do you know, so what kind of fields are we talking about?
I would have to look, but if you look at any paper by Dan Kleckner in the 90s, you'll see this technique used.
Okay, interesting. What most people do, and the reason I think that our results are so different from what most people have found, is they pass H2 over a hot filament, and then they have atomic hydrogen impinging on their surfaces. And they can either accelerate it or don't, but they have some flow of gas that goes over a hot filament to crack it, and then it hits the surface later. So that's the main difference. what we've done and what other people have done.
In forming the graphene, do you think there's any problem with hydrogenating both sides of the graphene sheet, or are you getting just the top surface?
It's very unlikely that we're affecting only the top surface. That people have shown very good interpolation of big things like lithium underneath graphene, between graphene and copper. It could be a little bit different in our case since we grow in UHV and those are grown at atmospheric pressure. So there are some variations in STM results of UHV grown and atmospheric pressure grown CVD graphene because of the interface between graphene and copper in the CVD case. So there may be differences because that interface is probably really important. But we see no reason to believe that graphene is so good at sealing the surface that hydrogen can't get in there. Yeah.
Can you do just height measurements and say it looks like the surface has come up in this area by enough to imply a hydrogen on both sides, or?
Yeah, we've tried to see if there's something consistent there that's independent of voltage, tunneling voltage or tunneling current, but then you get back to this problem where you're always measuring this combination of electronic properties and topography. So if you see a change in height, you don't already know which one it is. So one thing you can do is try to do DFT simulations to figure out, just try to deconvolute the two. But if you don't know where the hydrogens are, then you kind of are already starting another step back. So we do see changes in the height, but they're voltage dependent. So they're dependent on the tunneling energy. And it's not clear that there's a reason to believe that it's thicker.
You said your method had more order than previous method. I mean, as I understand, this is a layer of atoms on which you're putting another layer. How this disorder versus order defined you?
So what is the disorder in other experiments? Is that the question? So they were able to show that the hydrogen atoms absorbed at preferential distances from each other, but so this was an STM experiment, and there was no other, so it'd basically be a ring if you did an FFT. You wouldn't see points, you would see a ring. So that shows some order, but it's not a crystalline order. I'm not sure if that really answers your question. It's randomly distributed on the surface at some preferred distance is what people have seen previously.
Would you see any kind of tunneling or migration of the hydrogen if you did pattern it on graphene into the removed locations? People would say no. I don't think it's been shown, but the hydrogen is actually bonded to the carbon atoms, so you have to break that bond in order to remove it. And I think that it's not easy to do, but there hasn't been experimental evidence of this.
So you saw the shift in the tunneling of the surface mode when you had graphene on top of copper. So what do you see in the tunneling with graphene as opposed to graphene?
Oh yes, I think I might have a reserve slide on that. We don't see very much. We do see that graphene also affects the surface state, but it's pretty.
Does it at least go in the way you'd expect to have an insulator instead of a semi-metal on top?
I think you could make that argument, but after trying to understand the graphene on copper results, we realized that this is an interface effect that really is about the polarization of the two surfaces meeting each other, so it's not as straightforward as that, but maybe you can enlighten us, I don't know. So these are some of the results that we have in spectroscopy of the pristine graphene compared to the hydrogenated graphene. We have a lot of results, and I think part of what makes us convinced that this is real is that we were able to do this side by side on two regions with the same tip. So it's really hard to compare spectroscopy that we did yesterday to today, because we have to have some reference to say that this tip hasn't changed. Even a small change at the atomic scale on the tip can affect the spectroscopy. So it's a small shift. But we think that a lot of the reason that we don't see a bigger impact is because of the nearby copper. And it's just basically clouding all of our electronic measurements.
Do you have plans for suspended, isolated, not on copper?
Not suspended, but yes. Otherwise. Should I move on to that? Are there other questions? Okay, so yes, part of the motivation for what I plan to do at UNH is to get away from this 2D material on metal sample. I think there's some good stuff that can be done there. It's nice that it's all in UHB, but it's somewhat limited. So this is the system that I'm building up at UNH. It is an ultra-high vacuum and low temperature system. And it has two main chambers. It has an STM, actually this is an STM and an AFM chamber. It doesn't do cantilever AFM, it does something, it uses a tuning fork to do AFM, but it can do both. And then this is a chamber that has the same sort of tools that a traditional prep chamber would have, but it also has a fixed geometry. This cartoon you should take with a huge grain of salt. It's modified a lot since this. But it has a fixed geometry 4-point probe station to do transport measurements on flakes of two-dimensional materials without lithography. So one of the issues with lithography made two-dimensional materials is that it's really, really hard to get them clean again. And even the people that do a really good job and show that, you know, basically there's no doping, it's still pretty dirty. So this is the motivation here is to be able to do transport measurements on flakes, modify them in situ. We have an ion gun and an evaporator here. And we're also able to leak in gases and heat and cool. So we could do deposition and also potentially some chemical reactions in the chamber. And do transport characterization on in this side of the chamber, and then do atomic scale microscopy on the other side of the chamber. And because we'd be doing experiments of exfoliated flakes on insulators, they are clean and they're on insulators. So we should be able to get more information about from the Hollen spectroscopy. And then these little atoms with spins on them are to suggest that we can change these materials in situ and see what happens in transport and also on the atomic scale. And then the STM is also designed to be able to do simultaneous transport measurements and STM on pre-patterned devices. So like I said, devices are dirty, they're not ideal, but you can still get a lot of information. And I think there's a gap between experimentalists that do transport measurements and those that do these atomic scale measurements. So I would like to be able to correlate what happens on an atomic scale and on a device scale. This is part of the motivation for these projects. So let me show you the actual pictures. This thing was installed about 2 months ago. So this is the instrument in my lab. It's a closed cycle low temperature system. And so it's one of the first commercial systems that doesn't consume liquid helium, but is low temperature and can do scan probe microscopy. And the reasons, this was RHK in Michigan, and the reason that was difficult to do was because closed cycle helium systems have compressors, and so they shape everything. And so a lot of the engineering was in decoupling the vibrations of this thing. Now this is where the compressor sits from the atomic scale imaging that's supposed to happen down here. And they've done that. And a lot of the way that they've done that is the only thing that's mechanically coupling these together is this rubber bellows. And that rubber bellows houses, and the chamber below it, houses a helium exchange gas. So there's a cold head, that's a 4 Kelvin cold head, that extends into this empty chamber here. And then there's a low pressure helium exchange gas that cools the STM head. So this rubber bellows is the only mechanical connection to this compressor. But we were talking a little earlier about STMs and concrete pits and stuff. But you don't need a concrete pit for this instrument because it shakes itself. And so the STM is in this. Okay, so and then going back again, we have a load lock. We have this probe chamber, and we have a low T STM handler. All these things. Okay, so this is in the STM chamber. This is the shielded part, so that this gold-colored part in here is bolted to the bottom of the chamber with the cold head in it. So this is the low temperature end, and the tip in this instrument actually points up, and the sample hangs above it. So this is the tip near a graphite sample. And on this side of the chamber, this is the probe station that I was telling you about, and it is still in development. But the idea is that there's this V-shaped plate that we can modify to put different probes on the end. So what we can do initially is just put some wires there to make 4-point contacts, but that's not really the scale we want to be working at. So we are looking into designing a fibbed structure that has 4 forks that would be on a micron scale. And if you're working on a micron scale, this window isn't going to cut it. So we have this inverted window here that we're going to build a microscope in, and it can get within a millimeter of the sample. So we'll be able to have a microscope looking down on this sample in a micron scale, 4-point probe to land on these plates. All right. So these are all the people that I've worked with at Ohio State. I worked in the Center for Emerging Materials there with 2 faculty, Jay Gupta and C. Johnson Halgren. Jay Gupta's lab was the STM lab, and Zeke's lab does device scale work in spintronics. And these are 2 of the graduate students that did a lot of the work with me, and also an undergraduate student that did a lot of the spectroscopy type work. And then this is my new lab at University of New Hampshire. I have 2 graduate students in my lab right now. They're both second years, they're just learning a lot really fast. And I also have an undergraduate working with me. So with that, I just thank you for your attention and all the nice questions.
We had plenty of opportunities for questions. Are there any more last-minute questions before we conclude?
The copper steps, they don't appear all the same.
The same height?
Right. Not
Sometimes there are multiple steps,
Oh, okay.
but you often have single steps.
Do you get preferential growth of your graphene from the step edge of the copper?
We do get preferential growth from the step edge.
So you're kind of, it's always going to be in the worst possible spot.
Well, or the best spot, depending on what you're looking for. We've had some fun experiments where we had, and the graphene actually stops the copper from sublimating during the growth. So we can sometimes get pillars of graphene
On top of,
on top of a copper, and then all of the other copper steps are like down here. So some interesting things can happen. So, and then we also can preferentially, if we do the growth a certain way, we can get islands that are 10 nanometers wide. You can see all kinds of cool interference phenomena and stuff. So it's a whole, there's a lot that could be done here.
Technical question. Now, if you want to change a tip, do you have to take a system apart?
No, so in the system at Ohio State, it was pretty hard to change tips, but that's not true for me anymore. They're all right next to. This rack over here holds 8 tips, and to change them, you just open this door, pull that one out, and put that one in. So it's almost too easy.
So you do that under vacuum?
Oh yeah, we don't, and we can move the tips in and out of the chamber with a big long arm. So we don't break vacuum unless we have to.
And let's thank Professor Hollen again.